Good afternoon, good evening, good morning, depending on where you are watching us from. Once again, we are dealing with our lectures, our ongoing lecture series on how to use geomatics engineering to solve flooding menace. Um, Today, we are going to be looking at a typical challenge in Benin City. So we are looking at a section of ongoing projects where flooding has actually resulted to menace. So first and foremost, as part of this presentation, I'm showing you I'm showing you you know flood menace. You can see, look at the screen very well. You can see this is a residential section of the project we are dealing with. A section of it has the, and you can see the flood, the massive flood around this locality. You can see it. So we'll show you another video. I'm going to show you another video. You can hold on. If you look carefully, you see the water level. Look at the water level. I hope my viewers can see it very well. Then let's go to the second video. Let's go to the second video. So then can we check the other video, please? Let's check the other video. You can see how, see the menace of runoff. Alright. Then we have the third video, right? Let's check the third video. Okay, in the third video. So you can see that flooding challenge is not peculiar to any part of the world. I mean, flooding challenge is not peculiar to the location. It's peculiar. It's a phenomenon that is cutting across the entire globe. In as much as the rainfall is sustained for a period of time, and the infrastructural elements to take water to discharge places are not there, you are going to have flood menace like this. All right, can we see some pictures? Let's see some pictures. There are some pictures associated with it. There are some pictures associated with this. So, having said this, let's go back to our logical map. Can we show that a logical map? Now, of course, this is one method we are using to tackle the problem. Then I think we have the logical map. Can we have access to that? Now, first and foremost, what you are seeing like trees, these are actually natural flow paths within the project site. Natural flow paths within the flow site. We are trying to open up Google Earth, integrating it into the global mapper, the software we talked about last time, to see the map of the area of interest. Now, today, we are going to be doing this presentation or this lecture in collaboration with one of our trainees. Of course, yeah, this is the hydrological map of our study area. This is our study area. You can see the entire location is mapped as a map into catchments, has been designed into various catchments with various hydrological lengths can see the hydraulic lengths. Now, can we zoom to the beginning? Let's go to the beginning. It will interest you that this location is, for those of you who are in Benin City, this location is situated after the University of Benin main gate, Ubowo, before you get to Oluku. The popular evidence, you know the evidence Gospel Church. Can we zoom to that beginning? Let's be so that people will know. All right. Good. Can we do something? Can we position now? Can we just put, let's see, a typical, can we put, street view? Yeah, street view. Street view. This is Evident Gospel Church. Is it coming up? You know, in this part of the world, we have issue with, internet signals. The internet, the strength of the internet may okay. I'm trying to see if we can project the street view so that some persons who are familiar with this part of the world will see the area we are dealing with. Do not forget, we are discussing how to evaluate the quantity of flow using GEOMATICS engineering technique. The internet signal is not strong enough to display the street view. Because it's not strong enough to display the street view, let's come back to our plan view. All right. All right. The signal is not strong enough, so let's move on. Okay, now we are back to our hydrological map. Now, what are we dealing with? We are dealing with how to tackle the menace of flood. If I am to use the conventional survey method, I will spend 3 months or more trying to gather data, topographical data concerning these project sites. But with the advent of technology, with the advent of GEOMATICS engineering, I was able to have this location within 6 hours or less. So, what are we talking about? We're talking about how to take the whole quantity, how to compute the whole quantity into a single unit, a cumulated value of flow quantity, big Q. Let me use the word big Q. Now, once we are able to achieve that, the next thing we are going to do is to size a particular line drain that will take water from where it is now and send it to existing location within this project site. Can we have a look at, let's look at the other view, please. Let's look at the other view. Let's see the other view. Fine. Can we zoom out this section? Let's zoom out this section. Alright. Now, there is a section of this project site. It's a canal. Let me use the word canal. But in this part of the world, we call it moat, M-O-A-T. It's actually a natural occurring dish that will enable you, go the runoff from the study area. Now, the objective of this lecture is for us to, first and foremost, quantify the runoff affecting the project area. Then narrow it down to a location where we can now. Can somebody open up this view for me? Let's expand the view, please. Fine. What we want to do is to take advantage of this natural occurring dish to, you know, increase the storage capacity. So what we are saying here is that we need to size the discharge location, to size the discharge. To size the discharge location, you must understand the quantity of what you are bringing to the location you want to discharge water to. So that takes us to the preambles, the beginning, where we have to estimate or calculate or evaluate the quantity. Now, I am going to, the last time, my colleague joined me to carry out the presentation of this discussion. Today, one of our trainees is going to be given the opportunity to also tell us, because since the commencement of this training, we have actually subjected our trainees to rigorous, learning approach, though at their convenience, so that they can understand the right method, the right approach, the appropriate technique to do proper computation of runoff quantity. So, before me is Mr. Diamond, who is going to join me to talk about the computation we are trying to carry out today. So, do not also forget, we have our tutor, the lady civil engineer that taught us the last time. She is there. Then, of course, we have other of our trainees here who are part of the team. So, as a team, we are trying to see how to do things properly, so that in no distant time, everyone seated here can become part of how to compute runoff when you are dealing with how to prevent or control flood menace. So let me welcome Mr. Diamond to continue the lecture.
Good evening, everyone.
Good evening, sir.
Yeah, my MD once said, you see, this area is being affected by flood, but that's not just the case. As engineers, what we do is to provide solutions to every problem. What happened here is, for flood to occur, usually happen because of human activities. Most times, human activities. So, keep going. In this locality, being affected by flood, the first thing we do was to go into Google Earth. A GEOMATICS engineering software is one of the software we can use to easily locate any part of the world to Google Earth, and brought out the location, the area of study, which is Alibele. Yeah, Alibele. We brought it out. After bringing it out, we got some parts. You see these parts here. These are the consigned road in the area where we live. Went to Google Earth, brought out the image, and the second thing we did was this. Being that we know the area of study, how can we solve this issue of flood? First thing. Since we know how to solve it, since we got our area of study from Google Earth, from this area of study from Google Earth, what we did was to go into USGS to get a digital elevation model. Sometimes you'll be asking, what is the essence of digital elevation model? Now, the digital elevation model shows you the natural flow path of how this area of study is. From here, you see the digital elevation model. Can you please click on it to open it so you can have a view of how it looks like? Okay. Keep it on. Since we have imported our digital elevation model, after importing our digital, these are digital elevation model. Zoom out a bit so you can see the flow path. Please zoom out. No, zoom out. Zoom out. Yeah. You see this natural flowing path. You can see this is a digital elevation model downloaded from USGS. This is our study area, and these are the flow paths in blue. These are natural vegetations. You can see that the lowest part is blue, -9 meters below the main sea level. You can see these are flow parts. So the next thing is to analyze this area of study. How do we do that? By using this global mapper we see on, we go into the analysis tool and generate what we call watershed. After generating the watershed, it's going to give us different catchments and a flow path. These are the flow paths in view. Since getting our flow path, how does the water flow, how does this flow path affect this area of study? Zoom it. So,
Continue. Just continue.
how does it affect our area of study? Now, these blue lines called flow paths, they are connected to one another. It's like a bunch. There's a main branch. When you see a bunch of flow, a main branch with smaller branches, isn't it? Yes, they gather themselves and meet at a point and they move. These flow paths, one way or the other, develop to flooding in the locality, anywhere. For every part of the world, there is a natural flow path. So we are going to make use and take use of this flow path as an advantage to solve this flooding problem. These flow paths, they connected, cause flooding to the road and localities. So now, how do we solve it? We need to know the amount of flow, the amount of what is the flow we are talking, the quantity we are talking about. How do we solve it? There comes about a formula. We have a formula Q is equals to 0.278 CIA, where Q is our quantity of flow, or probably your discharge. You understand? Okay. Then this 0.278, if we say we should talk about how we got 0.27, it might take us a little bit of time. And remember, our main target is to solving this flood problem. Our C is the coefficient of what? Runoff. C, coefficient of runoff. Our I, intensity of rainfall. And our A is equals to what? The area of catchment. Remember, the objective is to contract to solve the problem of flood in this environment. But to do that, we have to apply this formula. For each catchment contributing flow to cause flood in this environment, we deal with them part by part. This is because we have to know the amount of water that catchment is generating to bring flood to this environment. The area is the area of the catchment contributing flood. Can you please the digitized image here? Put it on. Yeah. This blue, like I said earlier, if you watch very closely, the water goes down and keeps going down. It keeps going down. It keeps going down. This is our area of study. And for each color represent each catchment developing flow. So now, the area of this catchment is taken into consideration. Then I, the intensity of rainfall. Then we have our coefficient of runoff. We are going to calculate all that. But with time, we're just going to have a brief run into how we can solve our problem. That's what matters to us right now. Fine. Since we've digitized this, remember this thick blue line is the major flow path. This, the longest, is called an hydraulic length. You understand? Hydraulic what? Length. Stopping, why stopping? This is what we call type of concentration. We have the time of concentration. We have our return period. For here, we do make use of 25 years as our return period. The formula has been applied in order to have these formulas put in place to solve this problem. And these formulas are gotten from our highway manual volume 4. Okay, fine. Our time of concentration, I'm going to that. The formula is 0.604 RL over root x raised to power 0.467. Our TC simply means the time of concentration. Our arrow is, we're talking about our roughness coefficient. We are going to calculate with that. There are formulas in the highway manual. Maybe with time we can decide to share the manual for your personal learning. Then our L is the hydraulic length. Now, this is the as you can see, this is the highway manual. This is the formula, like I have stated before. Our L, the hydraulic length. Can you click on this, please? Click on the global map. So you see this thick blue line. This our hydraulic length. This our hydraulic length. Now, from this global map, this is our hydrological map. You can see that they are all leading somewhere. This is a natural occurring moat. We all know what a moat is, just like what our MD has stated earlier. And the design to stop and to ease this flooding menace is that this water from each catchment through the hydraulic length are going to come through this line straight into the moat. This moat is natural, like a natural drainage that brings water from each catchment. And this area, you see that water one way or the other goes into the moat. But you ask us, why is there still flood after having a moat? Like I said, human activities. We'll go there. So back to the formula. We have our TC, the time of retention is 0.604 RL over root x raised to power 0.467. Our arrow, like we said, is roughness coefficient. Our L is the hydraulic length. And our S is slope of catchment. Now, someone will be thinking, what is this slope of catchment this young man is trying to say? This is our hydraulic length. Our L, isn't it? Fine. Let me just clean it so we'll easily see what we are doing. For each part developing flow, for each catchment, so what we did here now is, after getting this hydraulic length for each of the catchments, we saved this as a layer and imported it as a data in what? Google Earth. The reason for this is this. Go back to Google Earth, please. Remember, our slope, S is slope of catchment. The reason for this is our slope has a formula actually. Our formula for slope is what? The H mass minus the H mean all over what? The HL. The HL is the hydraulic length. Now, is this okay? Go ahead. Can you please show me the elevation gradient? Yes. Yes, of that hydraulic length. Okay, fine. You see, we are still solving. Okay, from here you can see that the length of this hydraulic length is what? Is 417 meter. The length, the distance, 417 meter. And from this hydraulic length, the lowest is what? 122 meter, which is 0.122 kilometer. Then our highest point here is what? The H mass 126 meter, equivalent to 0.126 kilometer. Fine. So let's bring out our H mass. I'm just taking that hydraulic length as a case study now. Our H mass was is 0.126 kilometer. Our H mean is equals to 0.122 kilometer. And our hydraulic length, what was the hydraulic length? Is 417 meter. Knowing the fact that our hydraulic length is 417 meter, do you think we should solve with that? No. We have to convert that meter into a kilometer. How do we do that? Dividing through by what? 1000. So 417 meter divided by 1000 is going to give us 0.417 kilometer. So our HL is equals to 0.417 kilometer. Now back to our slope. Our slope simply means that H maximum minus the H minimum all over the HL, which is 0.417 kilometer. So we have 0.126 minus 0.122 all over 0.417. Can someone punch it into the calculator and give me a figure? Okay, thank you. Okay. Now, 0.0096. Now this is our slope. Fine. Remember, our HL is equivalent to our what? L. Isn't it? Hydraulic length. And what is the value we had? Hydraulic length is what? 417, which is 0.417 kilometer. 0.417 kilometer. Isn't it?
Yes.
We've gotten our slope. Remember also our time of concentration is 0.604 open bracket our RL all over what? The square root of our slope 0.467. Is that our formula?
That's our formula.
Very good. Now we're going to impute these formulas into it's just a long process how we solve our problem, which is going to be just a little guideline the things we do in the office to solve our problems. Now, can someone impute it? We have our time of concentration is equal to 0.604. Open your bracket. Our arrow is what? Just assume the roughness coefficient is probably gotten from our highway manual, and let's assume our roughness coefficient is 0.13. Okay, 0.13 times our hydraulic length here is 0.417 all over what? Our slope
is square root of 0.0096
raised to power 0.467. Are we correct?
Yes.
Punch it into the calculator.
Yes.
0.268. Okay, our TC here is equal to 0.268. Simple as that. Now, we've gotten our TC. So we'll be asking this retention time, time of concentration, time of what are we going to use it to do? Now, there are a lot you can do with it. There's this hydrological map for Benin, for rainfall in Nigeria. Benin happened to fall in zone 2 in that map. It's also in our highway manual. Can you check it, please? Okay, fine. Zone what? 2. Isn't it?
Yes.
Zone 2 now. Without further ado, the highway manual there is a precaution of the table 4.1 or 4.6. It shows us that. Okay. Can you go to that manual, the part of the manual, please? Yeah. Okay. Okay, here. Okay, fine. Okay, let me drop it so you can see. Zoom down, scroll down a bit. Let's see. Okay, now, from 2. So, from here, this zone, beneath zone 2, right? Okay, now. Our time of concentration was 0.268, right? Good.
intensity formula.
Yeah, I think it's
Yes.
yeah. Okay, give me
This is the intensity
yeah.
formula. Okay.
Okay.
Mathematical method. So intensity
Okay.
formula.
You state that. Okay, our time of concentration is 0.268. Let's write it somewhere. So, I'm going there. TC is equals to 0.268 in hours, remember. Okay, it's not up to 1 hour, remember. Okay, now, our intensity. Therefore, intensity we're talking about, you can see this is the formula for intensity. Our x is equal to beta plus y into 1 over alpha. Now, let's put it down. We're not going to run through the long process of proving how we got about those formulas. Go back to scroll up a bit. This TC is what we're going to use to calculate for our what? Intensity. Remember our TC, time of concentration. Remember as well, our Q is what? 0.268 CIA.
7
CIA. Our C is coefficient of runoff done. Yeah, we'll calculate from that. Why calculating for that? Time to use human judgment. If you see the side, you check. The buildings here, are they industrial building? Are they private building? The land, what is it for? Take that into consideration before you calculate for your C. Yeah, all long story short. So, we got our C. Our area is the catchment I've shown you earlier. There is an area for that catchment. Bring it out. But this intensity, how do you get this intensity? First of all, we have to find the type of concentration. The time of concentration we calculated was 0.268 hours. Now, get our beta alpha. We are still coming to this y. Our beta now. This is zone 2 Benicity. Zone 2 Benicity. Our time of retention is 0.268. 0.2, right? Do I have 0.268 here? No. 0.4. Okay. For accuracy, this is what we do. Don't have 0.268. Engineering mathematics, what we do is interpolation. We interpolate. How do we get to them? Do you want us to go into that long process?
No.
Okay. I know you are acquainted with that already. Fine. So we'll calculate to get our beta and 1 over alpha. Now y, there is a formula. Scroll down to that. Scroll up.
1 over alpha is 23.537.
Okay. Okay. From our calculation, our beta is what?
103.97.
103.97. Our 1 over alpha is what?
23.54.
23.54. Okay. Then our is what? Remember our retention time is what? 25 years.
Yes.
You understand? So when we imputed the formula, we got a figure. What is the figure? Where is the calculator? 3.199. So include these values into this intensity. What did you have as your answer? Intensity is what? Intensity is what? Someone will be fast about it. Substitute the values. Our intensity is what?
179.27.
Pardon?
179.27.
179.277. Fine. These are our intensity. Very important. Yeah. Take importance your units of measurement.
Yeah.
Very important. Okay. Yeah. So very good. So we've gotten our intensity. We've gotten our coefficient of runner. And we've gotten our area. What was the area of our catchment?